I'm delighted to be here at Georgia Tech. I'm a little confused at the moment as to who my audience is, because I see some people here, I see some people over there, and then there's apparently several people on Zoom as well. Okay, well, okay, but I'm here for you, okay? So, right, so that this is really about my talk. This is whatever. So I would say for those of you in the real audience, or any audience for that matter, please ask me questions or interrupt for clarification or whatever. It's like I don't want this to be just, I don't want to be a talking head. I want to try and actually sort of convey some real stuff. Okay. All right. So the title of this talk is Level Set Geometry and the Performance of Restarted-PDHG for Conic Linear Programming. And I would just have to say at the outset, so why do I underline my name here? I underline my name because I'm the speaker, okay? But I'm number 2 here because this work is really, I would say, the key ideas, the key effort is my fourth-year doctoral student, Zikai Xiong. And so I just got to do a shout out for him. And probably since I have your attention at the moment, if any faculty are here, he will be on the academic job market next year. So I just have to say that. Okay. And then I also say here, the paper will be available very soon. All papers are always available very soon. So that needs to be taken with a grain of salt. Okay. All righty. Now this is supposed to click. Ah, okay, so it's definitely got a delay, or maybe I need to point it. I might need to be pointing it over here. I don't know. Okay, so let's just do a very quick history of optimization in a sense, not meant to be comprehensive, but I would say for linear optimization, or often it's called linear programming, right? The simplex method was developed by Danzig in 1947. So that's actually 76 or 77 years ago, depending upon how you count. And that was the primary tool that we used to solve linear programs. It still is one of the primary tools. The other tool being interior point methods, which were really introduced to the world in 1984 in a paper by Narendra Karmarkar, although he was not doing what we now call interior point methods, which is follow a central path or a central trajectory to an optimal solution. But his work quickly led the way to that. Okay. There. Okay. And then the question is, okay, is this the state of the art? And is it going to be the state of the art? And of course, we don't know. Okay. But I would think that I would say there is some emerging stuff really just starting literally last year, okay, in what I would call huge scale methods for solving very, very large scale linear programming problems. And today I'm going to talk about that and their extension to conic problems as well. Okay. Yeah. So I say here, right, the next methods designed to address huge linear programming problems are really going to, I don't know what they are, but I think they're going to be first order methods that are primal-dual in nature, that are going to look a lot like what's called PDHG, or primal-dual hybrid gradient. Okay. Let's see how this works. Yes. All right. So, but whatever they're going to be, there definitely have to be first order methods, right? Because these problems are at the size and the scale where inverting a matrix is out of the question. All right. And some of these methods have commercial versions. Some of these commercial versions are quite new. So about a year ago, Google developed a method that they put in their OR tools. This was a team led by Miles Lubin, David Applegate, Hai-Hao Liu, and several others. I mean, Hai-Hao is at the University of Chicago, but spends a lot of time at Google. And then I would just say literally just a couple, oops, what did I do? Oh, yeah, okay. Just a couple of weeks ago, February 12th, so this first state-of-the-art commercial solver using first-order methods. There's a company called COPT that's, I think, based in China, and is I would say has academic roots, both at the moment to Haihao Liu and also Zikai Xiong, who's my doctoral student, and Yinyu Yi at Stanford. Okay, so first order methods are ideally suited. We really have the gaming industry to thank for this, because GPUs are now very, very sophisticated. And so the ability to do small scale parallelization is key to the ability, plays a very, very important role in first order methods for giant scale problems, and that in a way that second order methods or simplex method, anything that has to factorize a matrix cannot take good advantage of, okay? And so the method that have been really emerging is primal-dual hybrid gradient. I'll just refer to it from now on as PDHG. Sometimes it's also called the Chambol-Pock method. It was really first, I would say, both introduced and then beautifully studied in a paper by Chambol and Pock. I mean, just beautiful. Let's see if we can get this. All right, so I say here, PDHG is very good at solving large LPs. All right, now if you take a look at this, so this is I would say, a convenient plot, okay, that I believe has some flaws in it, okay? But this is sort of saying, if we look at, we looked at different, in a paper by Jinwen Yang and Haihao Liu, they looked at PDHG versus Gurobi, which is an advanced optimization software package that you can do primal simplex, dual simplex, and a barrier method, or an interpoint method. And we see from this that it's sort of the number of non-zeros in the matrix A grows, right? So that has emerged as sort of the modern metric. It's really not the dimensions, it's the number of non-zeros, okay? Because it is. And we see that PDHG just outperforms everybody in terms of as the problems get bigger. I'm not a great fan of this chart, to tell you the truth, in this paper. I believe it's a little deceptive because the termination tolerance is 10 to the minus fourth. And I would say by traditional metrics for solving linear programming problems, that is not a good tolerance, okay? But that will work to the advantage, of PDHG in particular, okay? So I'm looking at Pascal, and I see you're grinning when you see this. All right, so the goal of this talk is not going to be to hype anything, but I may wind up hyping something. But I'm trying to be academically honest here. Okay. All right. Okay. So huge scale LP and now conic linear programming research, I would say, has really had a renaissance just in the last several years in terms of first order methods. I just list a whole bunch of papers here but I'm really primal-dual hybrid gradient with restarts, and that's the Applegate, Oliver Hinder, Haihao Liu, and Miles Lubin. That was just last year. And then in December, Zikai Xiong and myself, we finally finished our paper on this topic. But today I really want to talk about our latest work, guarantees for PDHG for conic linear optimization, and then that's the topic of this talk. And I say the paper will be available, quote, soon, unquote. Okay. Good. All right. So now I'm going to show you actually the second to last slide of the whole talk. Okay. And so just to keep you interested. Okay. So I call this a sneak preview. This is a comparison of our method with a homegrown interior point method. Right. So we can't engineer our code the way Gurobi does. We're academics. We're not so focused on that. But we looked at a whole bunch of problems from the MIPLIB LP relaxations of the MIPLIB data set from 2017, and it's about 350 problems. And now we're trying to solve problems to an error of 10 to the minus eighth, which is a very, very sort of good tolerance for solving LP problems. And then this is the, say, like with a fraction, a runtime of 1,000 seconds, what fraction of these problems can be solved? Okay, and so you want your curve to be you want your curve here to be higher rather than lower. Okay, and so we looked at this. The purple curve here is a standard version of restarted primal-dual hybrid gradient, and that performs fairly well. And actually, the interior-point method that we developed just out of Nosadal and Wright's numerical optimization book, okay, that's the curve in blue. And then the curve in orange is our new method, okay, which doesn't do as well for problems that are easier to solve, but the problems that all codes have trouble with, which are the ones out here, after a while, we start to outperform even barrier methods, okay? Now, there is an asterisk here, which is there's a slight way in which we, I would say we're biasing towards us that I will get to later, okay? But I would say this was really more for proof of concept than anything else, okay? Good. All right, so now most of this talk, then I'm going to talk about theory for a while, and then I'm going to talk about then how theory is going to motivate some practical enhancements to the methods. So here we go, all right? So we're going to be looking at conic optimization, which is broader than LP, okay? And so the standard primal form is minimize the linear function, equality constraints, and X has to lie in a cone. And of course, our favorite cones are other than the non-negative orthant, is the second order cone and the semi-definite cone, of which the vast majority of convex optimization problems can be put into that form. And it has wound up being an extraordinarily relevant format. This format actually dates back to the 1950s, but I really have to credit Arkady Nemirovsky and for in a sense, I would say, sort of resurrecting the importance of this particular format for these particular cones, which he with Yuri Nesterov did in their famous book on interior point methods. Okay, so that's our primal problem. Then the dual problem looks like this, and K star is just the polar cone to the original cone, and we'll just take that as given information. And then we're going to take the whole thing and turn it into a saddle point problem. And I will be very honest with you, I never really studied saddle points problems for most of my career. They just seem to be sort of acute mathematical curiosity. But I believe it is this saddle point formulation that enables things to enables these methods to work so well. So these methods are actually designed for saddle point problems, not for solving primals and duals. Okay, so that is the fundamental structure. Okay. And sort of here is your canonical set. So here is linear programming as a special case. Here the cone is the non-negative orthant. And here's the more general convex concave saddle point problem, where I have a convex function here. I have the negative of a convex function here, and I have this bilinear term, okay? And you can think of, I'm trying to find, say, at this point, this red point here, which is in the saddle, essentially, okay? And here is, I would say, a naive updating scheme. So how would you do this? So you would sort of think the naive thing to do is, okay, let me take my y as fixed, and then let me then take a step essentially in the gradient of everything that's left over here. And that's really, in a sense, equivalent to what I've written down here with a step size of tau. Okay, and then do that, and then fix x So now that gives me xt plus 1. Now I fix x, and then and then since the dual problem is a maximization problem, then I'm going to minimize the negative of all of this. Okay, so it basically sort of says, and I think we even have some graphics that show this. So yeah, this is taking a step here, and then take a step in a different gradient there, and that sort of is the intuitive thing to do. But then we stayed here. This actually can diverge. Okay, so it turns out this naive scheme is a little too naive. All right, so in a sense that's because it's a saddle point problem. It really is not an optimization problem, or the two things are tied, sort of. They're composed together. Okay, but the following variation of that actually does converge, depending upon, of course, the choice of the step sizes. If instead of updating using xt plus 1, I take xt plus 1 plus also xt plus 1 minus xt. And sort of that gives me a little bit of history, and also just makes this more of a simultaneous problem to solve. And this sort of changes everything. Okay, and you might wonder why this 2 here, it appears a little mysterious, it's a little magical, and it really has to do with operator theory, and that this one operator, the norms of, basically the norm of the operator winds up being less than 1, okay, or the inverse of the operator winds up being less than 1. Okay, all right, and so this, if I apply that scheme with step sizes of tau and sigma to ordinary linear programming, actually, it's called primal-dual hybrid gradient. The iterates just take this form, okay? That I just do some matrix vector multiplication here, and then I take the non-negative part, and then that gives me xk plus 1, and then I just do this here, which is and so I say here it only requires matrix vector multiplications, and then I put simple in quotes that I think the original analysis of order 1 over t convergence, which is a sublinear rate of convergence, say was rather complicated. In just the last year, this convergence rate has now been, you can prove it much more easily in about 3/4 of a page, for example, okay, depending on your font size, obviously. Okay, and then it turns out that, so not only does this gets an order 1 over t convergence rate, but the step sizes have to be sufficiently small, namely the product of the step sizes for the primal step and the dual step have to be less than or equal to 1 over the largest singular value of a squared. Okay, and that's just a sort of a straightforward analysis. Okay, and so now I want to sort of motivate, instead of doing that, so do that for a while, then take the average of your iterates and then restart it. Okay, so this is called PDHG with restarts, or restarts for PDHG. And here's a visualization. Suppose this is an artificial problem. Suppose I'm just trying to solve the following min-max problem. Min over x, the max of y of x times y. The unique saddle point for this problem is the point 0, okay, that's where this star is. And if I initiate PDHG for this problem, okay, which with a small step size, okay, I get this curve. So it's just going to circle around. It's eventually going to wind its way there. Okay, all right. But if let me plot the average of the iterations. So the average of the iterations, as you can see here, is going much faster. Okay. Towards the optimum. And so if I instead sort of, I take a bunch, I go for a while and then I restart here, then I go even faster. Okay, so I run PDHG, I stop when I have a given stopping criteria. I take the average of all my previous iterations, I restart it. Okay, and then I do that for a while, take the average of these iterations and restart it, etc. Okay, And now before I show you a computational result, I just want to discuss something, and I believe this was due to Oliver Hinder or maybe Hai-Hao Liu. I'm not sure, but I think it first appeared in this paper. So how to measure the quality of a point in a saddle point problem. All right, well, there's a bunch of different ways, but the problem for linear programming is that sort of the ordinary way to do this is to define something called the duality gap, okay, which is not necessarily a duality gap, okay, but that's what it's usually called. And that looks something like, for a given x and y, I'm going to take the sup over all x hat and over all y hat of the difference of these two Lagrangians, right? In the case of linear programming, unfortunately, right, where life is almost always linear, okay, that this is going to evaluate to plus infinity almost everywhere, okay? And so it's not a good, like, if we had nice quadratic growth or stuff like that, it would be better, but because whatever, it's just too bad, okay? So instead, we measure things using something called the normalized duality gap, okay? Where instead of optimizing over all x hat non-negative and over all y hat, I'm going to say, okay, I want them to be close enough within basically their distance from the current point that I'm measuring things from is at most some number r. And then to compensate for that, I'm then going to divide by r here. And my norm here, I wrote down here, is an M norm, okay? And I'm now going to introduce a bunch of other notation for you. And in fact, I just might write this for you in case you're interested, just to have a list of notation. So I would say, think of Z is always going to be my X and my Y. And then later, I'm going to have W is always an S. Oops, sorry. X and S. All right. So the norm that I'm going to measure things with, and this is going to be on my Z variables, which is just the pair X, Y, okay, is the norm induced by this matrix. And it is just an identity matrix on the diagonal with a minus A and a minus A transpose, and those step sizes factored in, okay? And it just is. This is the way the theory works out, okay? That, and so that's my normalized duality gap, which I'm going to measure things. And so here's how my restarts. So I run my algorithm, say for k iterations. I'll let z bar k be the average after k iterations. And then maybe I wait till the normalized duality gap is sufficiently small. And I'm going to presume that my normalized duality gap has a nice growth property. And so I'm just going to show you what that property looks like, I think. Yes. Okay. So say, here's my normalized duality gap. Think of just as a measure of non-optimality, right? That's taking into account, you know, objective function gaps, infeasibility of primal and infeasibility of dual. So I just want you to, that's the way to conceptualize it. And suppose it looks like this. So here's at my optima, okay, the normalized duality gap is 0, and everywhere else it's positive, okay? And I want you to see sort of it grows away from the optimum at a certain rate. That growth is going to be alpha, and when alpha is small, okay, then it's growing very slowly away from there, and that's not going to be good, okay? But basically the way all the math works out is that I can have my distance to the optimal solution every 16 divided by alpha iterations. And so if alpha is big, okay, then I get closer faster, okay? And then if I do restarts, I'm able to get linear convergence, okay? I'm just gonna have you take that as given, or maybe you have some intuition in this just from these pictures, okay? So in the end, this kind of approach, if I satisfy this sort of normalized duality gap, this is like what's called a sharpness condition, So let me just draw that for you here in a way. Like, if I have a function, oh, that doesn't work. So if I have a function and sort of that function, say, here's its minimum and here's its growing away, and it satisfies a sharpness condition is if when I'm moving away from the optimum, okay, there's a nice positive angle here, okay? And the higher the angle, the sharper it is, okay? So if I have this sharpness in my normalized duality gap, say, I actually get a 1 over alpha log 1 over epsilon total complexity, okay? And, but of course, if the sharpness value is very low, then I'm gonna have a big constant here, okay? Okay. And then here is my scheme, and I think I'm just going to skip over some of this. Is just describing intuitively what I just sort of said. We run it for a while. We need a way to decide when I restart. And turns out that's relatively easy to do. Okay. Yeah. And so here's a current theory for PDHG for linear programming. And so I say here, PDHG has global linear convergence for LP instances because of this, and restarted PDHG is faster than standard PDHG, both in theory and in practice. And I would say we're very interested in theory because I always am interested in theory, but I'm interested in practice because we're doing linear optimization, and we're doing convex optimization. And if you're not coming up with methods that are actually going to work on real problems, I don't know what you're doing. Like, it's just, even as I worship at the sort of at the altar of theory, I'm very mindful of practice, okay? So those are the pros. I would say the cons is the current theoretical complexity that I just showed you is kind of loose, and it's also hard to compute and validate. That is, the theory sort of says, okay, this normalized duality gap is sharp. We have no idea how to measure the sharpness. We can bound it by something called the Hoffman constant of the matrix A. If any of you know what that is, like, that is so hard to compute, it's not even funny. Okay, it's an NP hard problem just to compute it. Is that true? I think it is true. I just said it. It ought to be true. All right. So current theoretical complexity is quite loose and hard to compute. And also you can come up with easy problems that are hard for PDHG. And I will show you one very shortly. Okay. And so our goals really is, one is, can we get an iteration bound that is both tighter and easier to analyze and easier to intuit? Okay. And we'd like to understand what properties of these otherwise easy problems make them hard. And if we can do that, then maybe we can modify problems to make them easier through some kind of pre-processing. Okay. So here's a seemingly easy LP instance. So I'm going to minimize this objective in yellow, subject to the intersection of the non-negative orthant and this blue hyperplane, okay? And the solution is trivial to compute using either the simplex method. It's always easy for simplex method and interior point method to solve this problem. And the problem is parameterized by this angle gamma. Okay, and you can imagine that as gamma goes to 0, okay, this thing is going to flatten out here and is just going to get nastier and nastier to solve. And so let me just show you. So, right, this is a two-dimensional problem. Actually, it's one-dimensional, okay, trivial to solve by our favorite algorithms. This is going to be very difficult for PDHG, okay? So in their 2022 paper, the Applegate, Hinder, Haihao Liu, and Miles Lubin, here was their theoretical complexity for that instance as a function of 1 over gamma. So this is, this is like, right, 1 over gamma is going to, this is growing exponentially here. So I've got this in log scale, and right, and over here corresponds to gamma being very, very tiny. right? Meanwhile, the actual performance is much better than that, but it's still not very good, because when I get out here to 10 to the 8th, for example, PDHG is going to take over 100,000 iterations on this two-dimensional problem, okay? And so we can then ask ourselves, I mean, we know at an intuitive level, but can we be more precise, right? And come up with a theory that pertains to this and that actually maybe that we can improve on. Okay, so I say here, what conditions of P of gamma make it so hard when gamma is close to 0? Okay, and so I would say conditions, well, we see condition numbers, the relevant condition numbers that describe the state or condition of the problem, okay? And these are LP problems. So what condition numbers drive the performance of PDHG? Can we improve these numbers and so improve computational theory and practice? Okay, and so, by the way, this was their bound. Okay, this is actually the performance and practice in green, and this is our new bound. Okay, so which is, right, there's still a gap between theory and practice, but it is less so, at least for this instance. Okay, all right. So I'm now just going to tell you, I'm just going to show you 3 condition measures that are going to, yes?
It's just saying the theory of PDHG is like good, so it's saying, also saying like practically PDHG is not us.
So both can happen. That's right. So right. So I mean, mind you, this was an engineered nasty problem. Okay, trivial as it may be, but it shows that there can be a big gap in the theory of PDHG, but also that PDHG has a really tough time in practice on this problem. Okay.
You ran the interior point method, but it also
no, it'll solve it just like that. Okay, and one reason an interior point method will solve it so quickly, okay, is that in a sense the interior point method is almost impervious to whatever geometry it is given, because it is constantly redefining norms and transforming the problem so that the geometry of the problem is beautiful. Okay, and why I say that is it has to do with just knowledge of how self-concordant functions work and all this other stuff. Okay, but just, I can go into more detail on that later with you if you'd like. Okay. All right. So here's our problem, right? Minimize CX, AX equal BX in the cone. Here's the dual problem. S is going to be my dual slacks that are going to sit in the dual cone. And I'm just going to make the following assumptions for convenience right now, so that the primal and dual each have strictly interior, or each are strictly feasible, meaning there's a feasible solution here in the interior of this cone, there's a feasible solution to this problem where S is in the interior of this cone, that the rows of A are linearly independent, and that the objective vector sits in the null space of A. And all that just says is that basically you could think of the objective vector itself is a feasible direction, okay? And that's just for convenience, okay? And so I've got, so if I put the two problems together, right, I sort of arrive at the following, which is I basically, if I combine the primal and the dual and I say, okay, X has to sit on this manifold, satisfy these affine constraints, right? My Y and S, or just S if I want to think about it, has to sit in this affine variety, and X and S together have to lie in a cone. And so here I have the combined cone of the X's and the S's, and then on the right, I have the affine space that they both have to sit in, okay? And so I can conceive of, in the space of my cone variables, which are X and S, that I'm just have to lie at the intersection of some cone in 2n-dimensional space and some affine, some linear equations or an affine variety in there, okay? All right, and then based on that, I can talk about then, I could talk about primal-dual sublevel sets, okay? So my duality gap will be a linear function of X and S. The optimal solution set, W star, Okay, that's going to be the set of optimums. So here I am in X and S space, right? My optimal solution, say, is at this point A. So that is the set, but more generally, it doesn't have to be a unique solution. And then I can also talk about that I can look at the sublevel set. So I can sort of say, okay, give me all X and S's that are primal and dual feasible and whose optimality gap is less than or equal to delta. And that's going to be this yellow region here. And now that once I have that region, okay, all right, that's all nice. And I'm going to talk about three different objects. One is, for a given delta, what is the diameter of this set? Okay, and that's going to be capital D sub delta. Okay, and I'll always show it in red. Okay, so that's going to be one condition number. Another condition number is going to be what we call the conic radius of this. It basically sort of says, okay, here's my sublevel set, okay, at level delta, okay. Find the point in this set that is the farthest from the cone, okay. And so that's might be this point right here. So its distance from, say, the cone, which in this case is the non-negative orthant, is the farthest. And that's called its conic radius, okay. So that is that. And then last of all is what's called the Hausdorff distance of the level set to the set of optima. And so that's going to be the point in the level set that's farthest from the optimal solution. Okay, all right. So that's the DH is the Hausdorff distance, right? And so let me show it. So I'm looking at the time. Holy cow. Okay. So you want me to stop roughly at 1, right? Huh?
15 minutes.
I have 15 minutes. Okay, well, all right. So this is going to be, I have an ordinary notion that I'm going to slide over quickly of what it means for something to be an epsilon optimal solution. Okay, and so here's my theorem. Okay, and this I call a composite computational guarantee for conic linear programming. So, and I've written it this way. So if I start at the origin, the number of PDHG iterations required to compute an epsilon optimal solution will be upper bounded by this quantity. So kappa is just going to be actually the condition number of my A matrix, okay, which I will get to shortly. And then, whoops, shoot. Yeah. And then here I have, okay, it's going to be the ratio of the diameter to the radius of my delta level set, that multiplied by a term, this is the linear convergence piece, and then my Hausdorff distance times this term, which is going to be the size of the optimal solution set, distance of the, basically the size of the smallest optimal solution divided by epsilon. And this is going to be my sublinear convergence. Okay, all right. So I call this composite because if this number here is big and this number here is really small, okay, then I'm mostly getting linear convergence. And vice versa. If this number is small and this number is relatively big, then I'm really got sublinear convergence, okay? But what delta should I choose? This is true for every delta, okay? For every sublevel set, okay? And so actually, I can choose so let's let T delta be that function, okay? So now I'm just going to write it this way, okay? In fact, it's going to be the best, okay? And so it's going to be the best of all of these because it's true for every one, all right? I get it to be the best, all right? And so let's just see what that looks like a little bit. Oh, now I've added color here, right? So again, this is my diameter divided by radius, conic radius, and here's my Hausdorff distance. And we're going to see how some of this works. Okay, actually, I'm going to, wait, where did I have my, sorry, folks, getting a little confused. Yeah, oh, here, that's right. And here again, this kappa is just the standard condition number of the matrix A, okay? All right, so let's just see a very small example, okay? So here's a small LP, 3 variables, okay? Obviously engineered, okay, to behave a certain way, right? But first of all, the Hausdorff distance has to be monotonically decreasing as delta goes to 0, because the sublevel set is just turning into the optimal solution, right? So that's going to be going to 0. And if I plot it, it looks like this. So now I'm getting delta is going to 0 as this goes to the right. This is right. This is going down logarithmically in scale. Okay. All right. And so, right, other things being equal, when delta is really small, this is great because my sublinear piece is going to be small. Okay. But it could be the case that my ratio of d delta over all delta might still be large. Okay. And here is that plot for this example. And so, in fact, it settles down, even as delta goes to 0, to be roughly 10 to the 5th. Yes?
So, so you don't require your iterate of the PDHG algorithm sit in the sublevel set, because I just didn't get the point why data can be any speed.
Okay, so I have a figure I can show you. So I think very highly of Zikai Xiong, okay, who developed this theory by basically looking at the relative sharpness of sublevel sets. And so this is not to get a delta optimal solution, okay? This is just sort of saying, if I just look at my delta level sets, I can get a better complexity bound.
Yeah,
Okay, so
data is a measure of the sharpness.
that's right. That's right. That's right. Okay. Yeah, so I can choose the best of all these bounds. So watch. And so, for example, if I choose delta equal 10 to the minus 1, here is my bound that I get, okay, as a function of my desired epsilon tolerance. This is epsilon, not delta. Okay, so this is my LP. This is my LP tolerance. Okay, all right. So that's delta equals 10 to the minus 1. Right. I could instead do delta equal 10 to the minus 8th, and I get a different bound. And then I can just sort of, now I can sort of think, well, okay, actually my actual bound then is going to be the minimum of these guys, okay? But I could try a whole bunch of different ones as well, and it's going to be the infimum of that whole envelope, okay? And so let me just show you what that looks like here. That's the orange figure, the orange line. And how does PDHG perform in practice for this problem? Well, I'm just going to show you, okay? That's in brown. And so it's not that far off from this, okay? So in other words, the bound is a little more complicated, okay? I can sort of say in its very, very worst case, it's going to be sublinear, okay? But it's richer than that, and also suggests that we might do some fun things, okay? All right, so notice, of course, this says if I can find a delta for which this is small and this is small, I'm going to be a happy person. Okay, I can't guarantee that's going to happen. In fact, I can artificially create problems for which either one of these, say, will be exponential. Okay, so in other words, this is not a perfect theory by any stretch of the imagination. It's not, even that's not it. It may be a perfect theory, but I'm just sort of saying it's not an optimistic theory. Okay, is a better way to put it. Okay, all right. And then, and then I just want to show you that, so you want to think of, in the case of linear programming, I can actually just get linear convergence because whatever, but I just want to show you this. Here's a linear programming problem for which that normalized duality gap is nice and sharp, okay? There are very many problems out there for which that normalized duality gap, you know, is like the sharpness here is like 2 to the minus L, okay? In which case I get linear convergence, but at a horrible rate. And for conic problems, I might not have any sharpness at all. Okay, so just want you to know that. Okay, all right. And so, all right. So this is Zikai's, the way he got all of this, but I'm going to skip over this. And for linear programming, actually, we do get linear convergence, but I don't have time to go into that. Okay, all right. So yeah, I'm gonna, all right. So I think here's what I'm gonna do. I'm gonna skip over a bunch of my other results, okay, which is unfortunate for me, but maybe fortunate for you, okay? So now I'm gonna talk about using theory to develop practical computational speedups, okay? And so here's the idea. Say here was my problem originally, okay, and say this is a linear programming problem. And I just want you to see the optimum, there's multiple optima, okay, and but say, think of this has very poor sharpness by anybody's definition of sharpness. Basically, that means like I can be very far from I can be very close to the optimum, optimal solution value, but very far from the set of optima. Okay, all right, so that's sharpness. All right, now, suppose I pick a point on the central trajectory using a barrier method. Okay, the central trajectory has amazing properties, and it gives us Hessian information that can be used to do incredible linear transformations. Okay, and so I don't want to get into it, but basically there are ellipsoids here that have very desirable properties that if I use those ellipsoids and I do a linear transformation to turn them into a ball, so here I'm doing here, I use some other first order method somehow to get a point on the central path, okay? I then compute these ellipsoids. I then rescale my original problem. Now my original problem is going to have very good geometry, okay? Those ratios and those objects there are going to be very well controlled, okay? That's the idea. So I do that first, then I run PDHG, okay? So the idea is compute a point somewhere on the central path. Now, mind you, that's not a trivial problem either, okay? But whatever, okay? So, and I can do this for linear programming, I can do this for SDP, I can do this for anything, okay? That is, the theory of self-concordant barriers pertains to all of this. And by the time you're done, I will just tell you, in the rescaled geometry, you get the following, which is the Hausdorff distance is, we're going to ignore delta bar here because this is going to, I can set this to be a nice small number if I want. And basically I can find a delta bar such that this Hausdorff distance term is low and just depends on what's called the complexity value of the barrier. And this ratio is 2 times the complexity value of the barrier. And for, say, linear program or SDP, this complexity value of the barrier is n, okay? And so what I've done is, and so everything is going to be nice and small and controlled, okay? So this is our strategy. Suppose we do the following. We do a rescaling transformation using a central path solution for a given pre-specified duality gap that you want, where on the central path you're going to be, okay? We also do some maybe row transformations to make the condition number of A 1. Then the number of PDHG iterations required is gonna all look good, okay? It's just gonna look very, very good, okay? These numbers that are pre-multiplying things here are just gonna be on the order of n. Think of it that way. And likewise, here's the n in the case of linear programming, okay? And I say here, we have replaced the ratio of diameter to the radius by the barrier parameter, which is the dimension, essentially the dimension of the problem, et cetera. And I say here, but of course, we're going to need to pay to compute this point on the central path, okay? And so here it is again, but now I'm just going to show you some computational experiments. So I'm going to measure error. George, now this is standard stopping criteria error for linear programming problems. We used MOSEC at first to solve the interior point method problem to see if it all is going to work. Okay, but eventually we're going to come up with our own problems to do this. Yikes. Okay, so here was a typical problem. Okay, so here was basic restarted PDHG with what's called easy column rescaling, okay, which I won't get into, but it's just a heuristic for rescaling columns, okay. Here, if we picked a point on the central path, right, with a delta value of 0.1, think of this is an optimality gap of 0.1, okay, all right. To rescale, right, instead of getting a tolerance of 10 to the minus 4, we can get down to 10 to the minus 6 very, very easily. Okay, all right. And if we pick a point even higher up on the central, well, lower down on the central path, okay, we can converge even faster. Okay, now we can easily get points 10 to the minus eighth after just a few iterations. Okay, so I say here, this is admittedly an unfair comparison, but it shows the potential for large speed ups in practice. Yes?
How realistic is it to do the rescaling?
Huh?
How realistic is it to do the rescaling?
The easy column rescaling? The other?
How realistic is it to do that?
How-
Because now you have to solve a linear system essentially. This.
Okay.
Getting back to
Yep. Okay, so what I'm going to try and do then is let me skip ahead and show you yeah. Okay, so here's what we did. Okay, so we randomly selected 153 LP relaxations from this set. Okay, now the problems are much bigger. Okay, well, m times n, 10 to the 3 is not so big, but 10 to the 12th is big. That's just the dimensions. Okay, and then we solved the central path solution using a conjugate gradient method. Okay, so actually we don't solve system of equations. Okay, so we used conjugate gradient and the standard interior point method in Nosedal and Wright's book. So in other words, we're doing first order methods, not using, so we're not, we're sort of solving system of equations, but we're using an iterative method, okay? Right? So we do that, then we run, so that's our conjugate gradient method. We run it 5 times to get 5 different points on the central path. Okay, so let me just draw this for you. All right, here is the central path. We get 5 different points on the central path. Okay, right. So, and we pick the best. We pick the point after the fact that got us the best result. Okay, all right. And so we're using first order methods throughout. Okay, so I say here we run this 5 times. We report the best combination additive, the interior point method runtime plus PDHG runtime. Okay, all right. And so this was our method here in orange, okay, on the 153 problems, all solved to a tolerance of 10 to the minus eighth, okay, compared to sort of standard reduced restarted PDHG with a standard what's called a Ruiz PC scaling, PC for Pock and Chambol, believe it or not. Okay, so we do much better than them, all right, especially out here. But the real thing is, how much better do we do than an interior point method? And so here is our interior point method. And this was the slide that I showed you at the start of the talk. Okay, so interior point methods are pretty phenomenal, but these are tough problems because they're just so big. Okay, and the reason why we only solve these 153 problems, all right, is basically all these computation was very time consuming, but whatever. But eventually, for the more difficult problems, okay, we outperform the interior point method clearly. Okay, but I say here, these problems here, even the ones out here, are still in a sense are in the comfort zone of interior point methods, but rescaled PDHG already looks better, okay? And as we go out and try and solve bigger and harder problems, for many of these, like MOSEC can't even solve it, okay? Because it has to store and try and factorize a giant matrix, okay? All right, so recap and takeaways. Okay. Convergence rate of PDHG on conic linear programs is related to the geometry of the primal-dual sublevel sets measured with those 3 condition numbers. Okay. Rescaling using a central path solution can improve the geometry of those numbers. Okay. And in fact, will not just improve, so it's what I say, it's sort of theory motivating computational practice. We used a first order IPM to compute a low accuracy central path solution. And then we used PDHG to finish it off, okay? we observed that first order methods can compute solutions of the same high accuracy as interior point methods. Our results actually relied only on two properties of PDHG, theoretical properties. They have to do with non-expansiveness of this operator, and similar results might also hold for other first order methods, in particular ADMM, the extra gradient method, proximal point method, et cetera, okay? But early on, like 2 years ago, the group at Google tested a whole bunch of different first order methods for solving LP, and they concluded that PDHG was where they wanted to put their research effort in. I never have seen, okay, so no one, I've asked, like, show me the results by which you, like, did PDHG outperform all these other methods, you know, hands down or on a majority of the, I don't know, okay? But anyway, we've been pursuing that. Thank you very much. I think this concludes my talk. Yes.
Question about the algorithm. So in the linear case, for PDHG, you have the primal projection, non-negative offset.
Right.
No projection.
Right.
In the Conic case, do you also have a primal projection on the cone?
Yes. Yeah.
Do you project on the dual cone as well?
No. So the PDHG is not a symmetric method. Okay. It operates differently, right? It operates differently with respect to those, to the primal problem versus the dual problem. Okay. You know, it's depending on your perspective, it's either that's a good thing or a bad thing. Yeah. Yes.
So due to rescaling, you first use a first order method to find this point.
Yeah.
Is there any way you can integrate the rescaling as part of like the standard PDHG
So,
solutions?
all right, say that again.
So rather than first doing the scaling and then running the algorithm, is there any way you can combine the two so that you keep rescaling during the iterations?
Right. So not yet. And in fact, I would say, right, we still do not have, we're working on this, but we would like to have a coherent theory or at least coherent heuristics that are going to sort of say, okay, you know, where should you go here? Where should you aim for, right? If you aim further down, you're going to get much better. You're going to get a much better rescaling, okay, right, than if you're up here. But getting down here is much more expensive, okay? And so, right, at the moment, we're just sort of literally doing, you know, sort of greedy testing, okay? But your idea is very interesting, which is, yeah, there's like, right, start way up here, but don't put too much effort into this, hardly at all, then improve, yeah. Oh, I like that, okay?
So the question in the chat, by the way.
Oh, okay, yes. Okay, thank you. I don't know, where is the chat? I'm a little, okay, so that might, oh, you know, you got the right
Yes,
one.
so can you give us an idea of the sizes of the LPs being solved in terms of N, M, and the density of A?
Yes, I can. Oops, yeah. So for these problems, okay, so M times N is in this range, okay, between the product of M and N between 10 to the 3 and 10 to the 12th, and the number of non-zeros was in this range, okay, so up to 10 to the 7th. Yeah. Yes.
A couple of questions. I know, like, you run interior point method with CG. So when
Say again?
you run IPM with CG as a solver.
Yeah.
Oh, but they keep running this, like, you know, they just use this algorithm.
Yeah.
Yeah.
And so, right. So, so CG for computing points on the central path, okay, it does good in here, but once you get down here, it does horrible. Okay, because these problems are increasingly just I want you to think that if I just think that what do the Hessians look like, right, or the ellipsoids right here? they're just getting flatter and flatter and flatter. Okay. And so, in fact, in the early days of interior point methods, right, AT&T in their Corbeck system, right, they offered a conditional gradient version of the method, but it was notoriously poor. Okay, because you can't use, or conditional CG methods just fail if you're trying to get accurate points on the path.
So another question is about this restocking, right? So because you don't know this alpha, you don't know the sharpness.
Right.
Also, you does not seem that you can compute the normalized
No,
gap.
wrong. So the normalized duality gap actually can be very, very easily computed.
You have a first semesters because you have min-max over all. Right?
Yeah, so but it and the M matrix, of course, is not diagonal, but it can be bounded from above and below by a diagonal matrix. And so then you just literally can it winds up being parameterized just by one scalar. That's all. So that's easy. And then we just restart when the normalized duality gap is halved. And that's how it's done. And that method works both in practice and in theory.
So your M is very special matrix that you can bound.
Yes, that's right. That's right. Yes. Yeah. Yeah. So I mean, yeah, it's like well, we're out of time probably. But yeah. I can go over this with you later this afternoon.
Any question?
Yeah.
You know, empirically, what happens when you don't have Slater condition on the primal-dual pair?
Yes. So I've skipped a bunch of slides on that. That's a really good question. I also really like it because I can answer it. All right. So So that very many problems, right? You don't satisfy that strict feasibility either in the primal or the dual or both. Okay. So, but interior point methods will even though they're not supposed to work, I mean, they work anyway. All right. But you can think of what they're doing as they are solving a nearby problem. And so that's exactly what we do, which is we solve a nearby problem, okay, and we get a point on the central path for a nearby problem. And then I would say, to a certain extent, we cross our fingers and hope, but it seems to work just great. Yeah, so even though I would say that there is no theory for that at the moment, right? I had slides that actually showed 70 problems for which the central path doesn't exist, how well we do. And we don't do as well as we do for the well-behaved problems, but we still do very well. Yeah.
There are no questions. Let us thank Robert for his time.
Yep.